Hi everyone. Today's recording is for Monday, March 30th. So welcome back from spring break. I know it probably wasn't the spring break we were all looking forward to, but at least we got to take a little break and get kind of used to our social distancing, etc. So today's agenda is going to have us looking at the chromatography notes. So this is essential question 5 in your interactive notebooks. We're going to be answering 2 questions. We want to know how are fibers collected forensically, and then our second question we want to look at is how can chromatography be used to separate and identify dyes found in the fibers that we have collected? I'm going to be moving our daily check-in to the end of this unit, so I'm hoping that you guys watch the video first, take the notes, and then do the daily check-in. If you didn't do that and you score poorly on it, go ahead and retake it again, and I'll give you the higher score. As far as our pride and our T cell, we are definitely prepared for college and career because you're logging in just like you would if you were in college. We're resourceful, working through this COVID-19 thing. We're going to make it, by the way. We're information literate. We're determined because we're going to graduate and we're going to celebrate. And of course, we're using technology. We're employable, life skills, and we're learning. So let's go ahead and move on to chromatography and fiber collection. And we see you have a picture here of chromatography. This will be in our video for tomorrow, but let's go ahead and move on. So on page 113 of your interactive notebook, you are going to be putting essential question 5. We actually have 2 essential questions here. The first one is choose the best methods for collecting fibers. So it's very simple. It's like a single slide answer on that one. And then our little more complicated question is going to be how do we use chromatography to identify fiber types and dyes? And so our pictures here, we have fibers. Again, if you don't remember, filaments are the tiny little threads or strands that are going to make up these threads. So this is a thread right here that we're looking at. And our threads then can be woven into fabrics, and our fabrics can be sewn into garments. On the right side here, we are seeing a beaker. We see several dyes along the side here. And then we see what we're going to later call a chromatogram that is going to help separate the dyes into their component colors. So let's answer that first essential question. So the first essential question, how are fibers collected? This is a really simple slide. I'm trying to go through and minimize as much as I can. So if we have a large item, like for example, this jacket here, it's got some blood. What we're going to do is we're going to hang dry that jacket. So you kind of see it hanging dry here. Once it is dry, we are going to then put it in a paper bag. So again, we see paper bag. You may want to go ahead and ask yourself, why is it a paper bag? And kind of going back to unit 3, we use paper bags because, especially since there was blood right here, that paper bag is going to eliminate the chances for mold or for mildew growing on that garment piece. So that is why we use our paper bags. What if it's a small fiber or a filament? So if we find a small fiber or a filament on a piece of maybe a body or on a sweater, something like that, we can use tape. So we see this right here, regular tape. Now this is not the normal forensic tape, but I just wanted to kind of get it into your head that it's tape. Could we use this tape? Yes, you can. The second option would be to use a vacuum. And so for the vacuum, we would have a special attachment to it, not this one here. This is an actual floor vac. I just wanted to, again, kind of get that into your head, tape and vacuum for collection. And then because it is a small item, it's going to be placed into an envelope. It could be into a small parcel envelope, like a small plastic bag. A regular paper envelope would be fine. And then you would place it in with chain of custody and submit that to your evidence tech. So 2 ways there. We're going to use tape or vacuum, and then we're going to store it in an envelope. If it's a large piece like our jacket here, we are going to use a paper bag to prevent mildew. So there's EQ1, that first part of that essential question 5. So what about if we're going to look at the dyes? So most fabrics are going to be start off either white or a natural color, like a beige maybe. And then they're going to be dyed to the desired color. So for example, like we see down here, maybe like this neon pink, you might have blue, purple, whatever dye you like. And so when they dye that, they are going to dye each bolt of fabric all in that same color. And we can actually use those dyes forensically to separate them, and we can determine what dye house they came from. The dye house is where they're manufactured, or what warehouse. And to date, we have about 7,000 different dye formulas. So that's a lot of dyes. I mean, just blue alone has several hundred different blues that you guys can use. But yeah, there's over 7,000 different dyes that your fabrics can be dyed. And the process for dyeing those is known as, I'm sorry, not dyeing those, but the process for separating those dyes into their component colors is known as chromatography. So I do want you guys to pay attention. Chromatography will definitely be on our test. So we definitely want to make sure that we know what chromatography means as you are taking your notes. Make sure you guys are highlighting that. Now, again, you should be chunking that. You do not have to write everything. Notice that I am trying to chunk as much as I can. You just need to write what you think is going to be important because we're going open notes on our tests. Then you want to write down whatever is going to help you get the highest score on that quiz, which is this Friday, by the way. One other thing that we can look at is how well does that fabric accept the dye. Not all fabrics can be dyed. Sometimes the pigment will actually have to be placed chemically into that fiber instead of dyed over it. And that particular way that that dye is accepted by the fabric is also something we can use forensically to determine what fabric that is or what dye that came from. So let's say your killer has a polyester jacket. He shed some fiber at the crime scene. We see that it's a black fiber. We separate that black fiber, and so we have a black pen right here. If you guys look, this black pen went through chromatography, and we see that black pen is actually made up of some yellow right here. We see that there's black, blue, kind of a lighter blue. If this dye combo is also shown in the fiber from the crime scene, and we collect the suspect's jacket, we also see the same color combo there. We can say that that is a match. It may not necessarily convict them, but if we have enough pieces of evidence, for example, we have fiber evidence, hair samples, things like that, that's going to allow us to have more of that class evidence that we can use for probability and probative value. So over here, we see a single chromatogram. So this paper is known as a chromatogram. We're going to pay a little bit more attention to it in just a second. But what we notice here is we have what's called an origin spot. So right there where I'm marking, that is the origin. And there is a line right here that is written in pencil. Pencil is extremely important. We never want to use a pen on a chromatogram as an origin marker. And the reason for that is that a pen will run. So if you're trying to determine your origin, you always use a pencil to mark this. Then you place your ink, probably in the center is a good place for it. You're going to place your ink in that center spot right there. This is our origin, very important. You place it into your eluting solvent. That is going to be the liquid that is going to separate the dye. You're going to notice here that we have lots of different component colors. So it started as blue. We see, though, that it has yellow, blue, pink, yellow again, and orange before it finally stops. If you look here, there is what we call the solvent front. So when the water basically runs out, we know that our chromatography experiment is done, and then we can go and determine what is known as retention factor. So that'll be on one of our next slides. All right. So again, like I said earlier, chromatography is a method for separating dyes into their components or their ingredients. I like to say it's kind of like ingredients. If you were to take a birthday cake and separate it, you might be able to separate it into flour, sugar, eggs, some type of oil, milk perhaps. And so chromatography, just like if we were to separate that cake, it's going to allow us to separate dyes. Chromatography is not only used for dyes, chromatography can be used for liquids. So let's say your killer has really has a fondness for Hawaiian Punch. They drink Hawaiian Punch at every crime scene. Maybe that's part of their MO. They leave that punch at the crime scene. We can do chromatography to determine what type of punch that is. So you could do chromatography for punch, like High C versus Hawaiian Punch versus Kool-Aid. Chromatography experiment could be used there. Chromatography can also be used to separate drugs, certain types of drugs, and it can also be used to determine whether or not water has been poisoned. We can use it for that. There's a lot of different applications for chromatography. But again, the main thing you want to know when you're thinking about chromatography is you want to remember the word separation. So it is a separating procedure here. Okay. And we're going to be separating them by molecular weight. So basically what that means when we say that we're separating by molecular weight, it means that the heavier molecules or the heavier components to your mixture are going to be at the bottom, and the lighter mixtures or the smaller mixture components are going to be at the top. And so over here in our diagram, we see a lot of stuff going on. We see lots of different colors going on. So one thing we can see is that we actually have multiple tests going on in this picture. And so I'm going to kind of reference these two vocabulary words, and then I'm going to tell you what they mean or where they correspond on the picture. So chromatography experiments always have two phases. The first phase is known as the mobile phase. You definitely need this for the test. So this is something you want to write down in your notes. And the mobile phase is going to be the liquid or the gas that is going to flow through the system. So in our system here, we see our container. We see our container is holding water or some type of liquid. This water is the mobile phase. So I'm going to label this as mobile phase. Kind of trying to write here with my mouse. So your water, this could be water. This could be a gas, depending on your experiment. This could be hydrochloric acid. This can be a lot of different chemicals. But whatever that liquid is on the bottom, that is our mobile phase. The reason why we call it the mobile phase is that this is actually going to be moving through this paper here. Looks like toilet paper, but it's not. It's going to be moving through this paper, and it's moving. So to me, mobile means to move. Mobile phase then means that it's going to be moving through our chromatogram. The stationary phase is part 2. And again, we definitely need this for the test. The stationary phase is going to be the solid, or it's going to be the card or the paper, whatever it is that you are putting your mystery mixture on, that is going to be your stationary phase. So for us, this could be paper or this could be gel. Because I can't get back onto campus, we're going to be doing this with a coffee filter tomorrow. If you want to do this for extra credit, you can. But if we had been in class, we would have been using a gel in what's called thin layer chromatography. So, but paper works just as well. This is going to be a coffee filter for us tomorrow. So this filter is our stationary phase. Why is it stationary? It's not moving. It's going to be still the entire time. So earlier I had mentioned that this particular chromatogram has several parts. So we have our mobile phase as part 1. Our paper up here, this is our stationary phase. So I'm going to go ahead and label that as stat because I don't want to write out stationary. Oops. So that's our stationary phase. Oh, I'm going to do it anyway. All right. And then we actually have what looks to be 5 different experiments going on here. So at what's labeled number 6 right here, we're going to call number 6 the origin. You definitely want to write this out in your notes. So draw this picture. So this number 6 is our origin. This is going to be really important when we do some calculations in just a minute. So 6 is always written, or your origin is always written in pencil. Very important. I just said earlier because it's not going to run during the experiment. So pencil, pencil, pencil for your origin. Now what you're going to do is on your chromatogram, which is our paper, our stationary phase, we are going to place, in this particular case, 5 different colors. So we have a black right here. We have, looks to be a dark blue, a green, a red, and a yellow. So these are unknowns. And in this case, we have 5. So for this part, we have unknowns. These are the mixtures that we are trying to test. Okay, so we're going to place them. When you place these, you only want to put a small dot. You don't need to put like a huge glob. about like the size of a pinpoint, or just taking your marker and dotting it on that line, that's sufficient enough to get this experiment rolling. You are going to place your stationary phase into the mobile phase. You want to make sure that the mobile phase is below this line. So if you dunk your stationary phase in and the whole thing goes underwater, you're not going to get an accurate reading of what your mixture is. So we just put the very bottom below the line into the water or into the mobile phase, and that is going to wick its way up using what's called capillary action. So capillary action is where our basically when liquids are kind of soaking their way up to the top of our stationary phase. And in that soaking process, they are going to separate. We know that all of these guys down here, these have the high molecular weight. So they're heavy. High molecular weight. I'm going to call that high MW for molecular weight. And these guys up here, they have a lower molecular weight. So they're smaller. And these guys here are in the middle. So high molecular weight is going to be at the bottom. Low molecular weight is going to be at the top. We have our intermediate molecular weights going in between these guys. And each of these chromatograms is a signature. It is individual to that particular ink. So this is a very precise method. You can use this in a variety of different techniques, and you're going to always get the same outcome. So if you always use a Crayola marker, you will always get the same chromatogram. If you're going to use a Prang marker or like the cheap Target brand, whatever, you're going to get the same molecular marker. So this is a physical property of a particular mixture or ink. And we will be doing these on our quiz. So we definitely want to make sure we understand those. So let's do calculations. So how do we calculate this retention factor? Retention factor will definitely be on your test. So again, you want to put a star next to that. This is a word you most definitely want to know. The retention factor, as far as definition is concerned, is a ratio. So that ratio tells us we're going to be dividing. So whenever we see ratio, we know we're going to be comparing two values, and most likely we're going to be dividing those two values. And we're going to be looking at the distance from the center of the spot for a given mixture to the distance traveled by the solvent front. So what we're looking at is we have what we call the origin. And here's our origin here. We have two spots. So this particular mixture, whatever color that was, like a reddish brown, was made up of two spots. We have spot 1, spot 2. Each spot will have a separate retention factor. To calculate that retention factor, we need to know the distance from origin to spot. So again, it's a ratio, so we're going to be dividing. We're simply going to take our ruler and we're going to measure from the midpoint of that spot. So for this particular spot, that's right here. This distance from here, that's ugly, but to there is 1.7 centimeters. The solvent front is where the mobile phase, in this case water, stopped. We know that the experiment is done because we're going to see this little V-shaped depression right here. So when we're looking for a depression, a solvent front, we want to see, did we get that V-shaped depression? If we have that V-shaped depression, we know that our experiment is over and it's time to calculate. So we do see my V-shaped depression there. I'm going to go ahead and erase this really quick. And now we're ready to roll. So it says calculate the retention factor for the orange spot. So we have spot 1 or spot orange. If the distance from the spot is 1.7 centimeters. So we know that the distance from origin to here is 1.7 centimeters. And the distance from the solvent front from the origin is 2.8 centimeters. So from here to here is 2.8. So we need to calculate that. So we're going to go ahead and use our guess method. And we know our guess method is, we're going to need a distance from origin. And I'm just going to put a little arrow here just to tell me where this is from. And I'm going to say solvent front, SF. And that distance from SF, from solvent front, is 2.8 centimeters. You can read that. And then we're going to do distance from origin to spot. And in this case, this is our orange spot, but I'm just going to go ahead and call it spot. So distance to origin to spot. And we know that that's 1.7 centimeters. So we do want to set up that G. For our U, we want to know what is our retention factor. So RF. For our equation, we know that retention factor is equal to distance from origin to spot. So we're going to go distance from origin to spot divided by distance from origin to solvent front. And then if you later on want to put just S and then solvent front, you can do that too. I'm just showing you guys where I'm going. So again, this is from here to here, and then from here to here. And so now I'm going to substitute those in, and I get retention factor, if I have room, is equal to 1.7 divided by 2.8. And let's see if anybody catches me and notices that I left off centimeters. And so right about now, as you're setting this up, you should have noticed that the centimeters are going to cancel. So this is going to be another one of our variables that do not have any type of unit. So if I put in my 1.7 and I divide that by my 2.8, I end up with 0.6, and I'm going to round that for significant figures, 1. So my retention factor is 0.61 for this particular mixture. So it's pretty easy, pretty straightforward equation, just a division. Again, it's a ratio, so whenever you see that ratio, you know it's going to be a division because we're comparing two values there. Okay, practice problem 2. So practice problem 2 is up to you. You guys are going to go ahead and calculate that out, and practice problem 2 is going to be part of your checkout today. So you want to make sure you guys do practice problem 2. Getting that correct answer will be part of your check-in. Just so you guys know, you get 2 points for checking in, so you could basically just bubble whatever you want and get automatic 2 points. However, you do want to start answering those questions correctly now because they're going to be worth a little bit more. If you answer more than what I give you, then you get the extra credit. So I try to make them about 3 points, so you're trying to get at least 1 point correct each day. Anything else I post is extra credit, and some of you have really taken advantage of that, so that's awesome. So practice problem 2 will be there, and then you guys will have 3 practice problems to complete for homework, so those will be posted as well. All right, so fiber evidence. In a court case, fiber evidence, again, we know that fibers are always going to be considered class evidence because of the fact they are mass produced. There really is no way to individualize those. We individualize them through usage. For example, things like getting paint on them, markers, stains, blood, things like that. But the fiber itself is always considered class evidence. For that reason, fiber evidence is always considered circumstantial. So class evidence is often circumstantial. What does that mean? Circumstantial evidence basically means that it implies a fact without proving it. So if your suspect has a red jacket, you find a red fiber at that crime scene, you can kind of say, well, look, you have this red jacket, there's a red fiber at the crime scene. It implies that that suspect possibly could have been a part of that crime. Doesn't prove it, but it does give you a little bit more probative value having that piece of evidence in your pocket. At the end of this week, and for extra credit, so there were some of you guys who did not finish certain labs, I am going to be posting a case study. So the case study was about Wayne Williams. This is a case that occurred in 1982. The gist of it is that Wayne Williams was convicted based off of carpet fibers that were found on the bodies of the victims that he murdered. He is a serial killer, and we were able to use those carpet fibers and link it back to Williams's property. I will post that case study with the assignment on there, and that will replace one lab for you. So in the event that you missed a lab or you did poorly on a lab, you can do that case study, and that will replace that grade. If you want to just do it for extra credit, or you want to just read more about serial killers, you are welcome to do that for extra credit to pad your grade. There are several of you who are over 100% right now, so I'm very proud of you. Finish strong. I know it's been a tough semester, but you guys can do this. Take advantage of all of these different opportunities, and as always, reach out to me. Don't worry too much. As long as it's not after 9 o'clock, I usually will answer your remind pretty quickly. If you need to conference call with me, you guys can do that as well. And then I'll be setting up a Zoom session this week as well. So that's it for fiber evidence today, chromatography and collection. If you have any questions, please message me. And as always, be safe. And I will see you again tomorrow.